All right. Hi, my name is Oleg Avdeyev. I work with Adderall, and I'm going to talk today about our experiences in building data pipelines using containers and Spot instances. I guess the container parts brought so many people here. Anyway, so it's mostly about the lessons we learned from building a new product on a pretty short timeline with just a few people. And it's, I would call it data heavy, or it's big data problem for us, and how we'll manage to leverage AWS and Docker to make it as simple as possible and with very little maintenance, and kind of manage to do this on a budget. So a little bit about the product we were building. It's called Adderall Prospecting. It's basically customer acquisition product. So advertisers, we're an advertising company, so advertisers opt in data. They have some anonymized user profiles, and they can leverage that to build audiences to discover new customers for their products. And if you think about this, this is kind of holy grail of advertising. Let's say you're selling shoes and your profit margin is $10. So you'd be totally happy to give $9 out of 10 to a company like Adderall if you manage to bring new customers to you and you still make a healthy profit. This is basically money-making machine. So we selling money-making machines. That's pretty good business if you manage to pull this off. And it's pretty data-heavy problem. We have hundreds of terabytes of data, billions of cookies, kind of anonymized profiles, and we're building about 28,000 machine learning models per day to make this work. So requirements we had for this system is, of course, it has to be robust. That means that it shouldn't require too much attention. It should be as simple as possible, even though there's really nice, sophisticated, mature products like distributed databases, like, I don't know, Cassandra. They still need someone to keep an eye on them. So we wanted to be as bare bones as possible without, of course, sacrificing performance and giving all tools to our data scientists and machine learning engineers to build those machine learning models. It had to be language agnostic. We're not big fans of getting pigeonholed into some specific ecosystem. I have nothing bad to say about Java, but we didn't want to get stuck with just Java stack or Python stack for all it's worth. And we have multiple people from different backgrounds on our team, like machine learning engineers, data scientists. We want them to use the tools they are comfortable with. So like Python, Julia, we use C for performance critical parts when it's just crunching numbers. There's still, it's a pretty simple tool, but works well for the last 40 years. And we have bits of Julia, and I think we have some bits of Haskell now. So really didn't want to get stuck on some specific ecosystem. It has to be easy to debug. This is kind of a trivial point, but you want people to be able to examine their jobs and see what's going on, why they fail, when they fail, to be able to easily pull off logs from their chunks of code they write. And it should be easy to deploy new jobs, not for engineers, just for data scientists, so they don't have to learn too much about deployment and things like that. So first thing is you want to run those chunks of code, those written in different languages. Specifically, R is pretty bad with their library management situation. So we wanted to keep it contained. So obvious answer this year, it seems Docker. Nice tool. Primarily solves deployment problem for us. So we don't really use any kind of resource management, multi-tenancy capabilities in Docker, like creating sandboxes and like limiting number of memory job using. We just want to like build this big, hairy tarball and just keep everything there and make it more or less reproducible. So for us, Docker kind of solves this libraries problem. It's kind of sweeping the problem under the rug because you build this crazy tarballs that you kind of accumulate. You don't know what's inside, but good thing you can still get an image and get it running pretty reproducibly. And you really don't want, I mean, you can, when you work in like pure software product and you have just software engineers, you kind of can make them follow some strict guidelines, building packages and setting fine-grained requirements and versions, things like that. But it's still hard. If you have data scientists, I have nothing bad to say about them, but I mean, they make good salaries, and I don't want those people to waste their time on deployment and like fiddling with versions and like version conflicts and stuff like that. So the best solution we have right now is just to build this blob and just ship it into data pipeline. Docker is hip, which is a big advantage because you actually seriously can attract more engineers because engineers want to work on new exciting stuff. So when you say Docker, lots of people show up. And it has great tooling because this is not new technology. Containers were there for a long time, probably tens of years. But what's good about Docker is that they have really good tooling around it. It's easy to use. And it has a lot of momentum right now. So this is an example of Dockerfile to build a blob. I guess most of you are familiar with Docker. I'm not going to focus on that. But you just describe your steps to build this container, just bake it. It's basically like AMI or something, or any virtual machine image. The advantage is that it's much more lightweight, and like startup times are much smaller. So the next problem you have is running containers. So you can easily run Docker containers on your laptop or wherever. You can start an EC2 instance, but when you're starting to do this at scale, and you have hundreds of containers running, you want to have some kind of orchestration framework. You don't want to manually provision all those instances. And there is a bunch of solutions for this. There is Swarm, which is Docker own tool, I think, which is still under development, I think. There's whole Misc ecosystem. There's ECS, which is we have really high hopes for, but when we started this, ECS was still in beta, so we didn't go for it. And you can build a custom scheduler or queue. I think there is like hundreds of queues right now. There's like RabbitMQ, like tons of them. And of course, we decided to build our own. And the kind of big point about Swarm and Mesosphere is that their primary use case is running services. So you want to have a fleet of containers running your web app or something like that. And not too many of them, at least not too much focus is spent on building this for the case of batch jobs, when you have containers running for like minutes to maybe a few hours tops. So yeah, we built our own queue service, which we may open source, but it's pretty simple. It's called Quentin. So it's kind of a middleman between CloudWatch and autoscaling groups that run Docker containers. It's a simple queue service. You just submit your jobs, like I want to run this container somewhere, sometime. There is no strict real-time guarantees because it's all batch jobs and we're kind of not too sensitive about delays. So what it does is basically keep this queue, sends the queue size to CloudWatch, so CloudWatch can scale autoscaling groups depending on demand. And that's a little bit different from normal, I guess, use case for autoscaling groups. Because when you're running a service and you just want to have some kind of room to spare, you don't want all your instances to run at maximum memory, maximum CPU. But with batch jobs, that's the opposite. You want to save money. I don't want to instances sit there idle. So we want to aggressively scale up and down depending on workload and keep them all busy. And if we have to keep a backlog or a queue, we're fine with that. So yeah, there is a queue, and Magic go to CloudWatch. It's really bare bones, not highly available system. Yeah, and it has some few good features which are kind of helpful when debugging it. So it captures standard output. There are lots of services to do that, and we kind of encourage people who create those jobs to actually feed their logs somewhere else if logs are really that important. But it's still, when you just want to play with the system, it's nice to have some kind of built-in capabilities to do that. And it has UI, which is also really bare bones, but looks like this. So just a job queue, but you can cancel jobs and examine their status and look like at standard output and cluster size. Really valuable tool for people who are using this. That's how our normal workload looks like. This is the number of instances in autoscaling groups. We're using largest instances because most of the jobs are pretty want a lot of memory. So we use R38X largest, and as you can see here, several times a day we scale from 0 to more than 100 instances. It's something like 30 terabytes of RAM total in the cluster. It's kind of getting big there. And a few lessons we learned from doing this is that, as I said, you want to scale based on job backlog size. We tried to do this based on cluster utilization. CPU doesn't work well. It just really, if you have 10 jobs in a queue, you want to start 10 or maybe 5 instances. You kind of have to be a little bit smart there because in EC2 you still pay for an hour. So if you just start an instance, run a 10-minute job, and just kill it, and then next job comes in, you kind of lose money. We have multiple instance pools because different jobs require different instance size. And integrate with autoscaling groups, it kind of starts to look like Spot Fleet, sort of. So we kind of have hopes for that as well. But still, there are some features missing. So for now, we're still using autoscaling groups and just multiple queues for different workloads. We use Elastic load balancing just for health checks. So there is no load balancing going on whatsoever. It's just basic EC2 health checks are like really basic. They just tell you if instance is dead or not. If you want something to kind of ping your instance and like maybe fetch a URL just to, if you have a daemon there, just checking for overall health. That's what we use Elastic load balancers for, but I think this becomes unnecessary with CloudWatch alerts. And we use lifecycle hooks to kind of work around the problem when you're trying to scale your cluster down. Let's say you had 100 jobs running. And then you want to bring it to 10 because there's only 10 left. But with that autoscaling groups, by default, autoscaling doesn't know what instances are you actually using. So it just kills random ones. You kind of get in a loop when they fail, and then they retry. So there's a way to do this with lifecycle hooks. You kind of send a heartbeat to autoscaling, like to keep those particular instances alive when scaling down. Things we found out we don't really need is data-aware scheduling and high availability. So as for data-aware scheduling, we just keep everything in S3. You can get pretty good bandwidth downloading from S3. So all the jobs just pulling data down, usually on ephemeral drives, process it, and put it back in. And we used to have some features in the scheduler that allowed us to kind of optimize that, like many jobs share same data sets. So if the job that just finished used some files and next job kind of wants them too, we would try to schedule next job on the same node so that it doesn't have to download data, but it's kind of hard to tune, and really you get pretty good performance out of S3, so we kind of abandoned this. And as for high availability, again, if you use S3, so kind of all the heavy lifting is done for you. It's already distributed, reliable system, so if you just push your data to S3 and pull from S3, your scheduler doesn't have to be highly available. And EC2 got much better over the next few years. I don't remember any instances just going down randomly for a long time now. So this thing just runs on a single server. There's not that much workload just to keep a queue and some REST API to submit jobs. So we didn't go for high availability. One thing that would be nice to have, which is not exactly provided by CloudWatch right now, is kind of job profiling. So when you have batch jobs, it's a little bit different from having a service running continuously. So you can see like CPU going up at 12 p.m. or something like that. With batch jobs, you just have lots of copies of same code, crunching data at different times of day. And what you really want to do is kind of see profiles in like relative time scale. So you want to see this job ran 1,000 times over the last few days, and it kind of starts to take longer or starts to use more CPU or hits operating system paging. So we have our own tools around this, but it would be nice if someone actually provided this as a service that would be also cheap. Next thing you want to look at is job dependencies. So when you have all these containers running, thousands of them, you still want to have some kind of layer on top that would help you to kind of coordinate the jobs. Because in our case, for example, you just pretty much standard data pipeline. You pull logs from somewhere. We compress them. We kind of get rid of the data we don't need downstream to reduce working set size. And you need some tool to coordinate this. And this is really like 50-year-old problem. So since like invention of computers, that was a big use case. This is 50 years ago, IBM released OS-360, batch processing operating system. So back then, you didn't even have any like interactive prompt or whatever. You just submitted your jobs as kind of schedules. And 50 years ago, they had special languages to describe those jobs, dependencies, do all the scheduling. So it's as old as computing, basically. And even before that, I think NASA had a system called PERT to also kind of job scheduling. And that when, for example, topological sorting algorithms were invented, and it was used to manage kind of manual labor. So they had to build a spaceship. Or actually, Navy also used this to build actual ships. So you kind of want to coordinate all the teams building different parts of it and assembly. So 50 years from there, today, in this season, we have multiple tools to do this. So there is Kronos, built by Airbnb. There is Airflow, built also by Airbnb. Apparently, they weren't happy with Kronos for some reason. There is all the continuous integration tools like Jenkins or BuildBot, which is kind of different beast in a sense, but also this is a system that schedules some chunks of code to run regularly. So they're actually pretty stable, and at some point, I think we used BuildBot for this, and I think part of the Adderall still use Jenkins, because it's pretty easy to set up, and it has GUI and everything. And there's a thing called Luigi from Spotify, which we ended up using, and I'll talk a little bit about it later. But first, I wanted to point out one kind of common pattern in those tools. So many of them come from a kind of cron-like approach. So you have a config file that says, I want to run this at 12 p.m. daily. It's kind of intuitive and easy when you have a single job. And then you start to have dependencies. And it's also a solvable problem. You can have job C. So like today, you run job A and job C for today's log files. Tomorrow, you run it for next batch for yesterday's logs. Pretty easy. You can have multiple dependencies, even though this is kind of harder when you start from like cron-like system. The bit of a problem starts when you have jobs failing, and that happens. And they get delayed, and then run over this midnight boundary, and now it's not completely clear. If you want to run this on today's data or yesterday's, it's kind of, it's not a hard problem, obviously. You can figure this out. But it kind of complicates all the pipeline, and people who use it kind of have a harder time figuring out what's going on, what went wrong, what has to be restarted. And yeah, you can have all kinds of failures there. So our solution is to just forget about time for now. You just kind of have this directed acyclic graph of jobs and dependencies. And instead of kind of building cron-like system, you basically have make as a build tool. So you just want to define inputs and outputs for every job. And basically, in terms of files, in our case, in files in S3. And you just tell it, hey, there is a piece of code I want to run to produce results from inputs. And it makes things really easy. You don't have to care about time and date anymore. You just consider it another parameter. And jobs are triggered on file existence, so there is no shared some kind of state in memory that system has to keep. And it's hard to get insights into it. If it's just some kind of magic objects in memory and it has some notion of job completeness, you don't have to do this if you just do make-file-like approach. You just rely on file existence somewhere, so like S3 or maybe database rows or stuff like that. And it's easy to inspect. You can just see the file is missing, then job has failed, or you can just restart jobs just by removing files, and they just pick up the next run, just sees that file is missing, and it will just restart parts of your pipeline. It works really nicely for us. So the tool we use is called Luigi. It's on GitHub, open sourced by Spotify. It's pretty much exactly Makefiles, except they don't have this 30-year-old craft. It's written in Python, really small code base, which is great. It's not too sophisticated. It's really to hack. It's really easy to hack it. So yeah, it has a bunch of libraries to work with S3 and Hadoop inputs and outputs. It's called targets, just out of the box. And you can write your own extensions in Python pretty easily. And it has UI, which is kind of lacking part, but it still has it, which is great. So you still can look at things, and people who write those jobs here and not necessarily have a lot of background in software, they can still examine what's going on there. So it's, yeah, exactly the direct acyclic graph like this. I think we have like thousands of nodes in our jobs running daily. Good thing about it, maybe opposed to Makefiles, is that you can create new jobs from other jobs. So you can just, let's say we can have a job that first looks at log files and then chart them by size to make things faster, to make things parallel. And it can create thousands of kind of child jobs. And Luigi just execute this, figures out what order they should run in, and takes care of all the dependencies. But yeah, it's really simple. This is how Luigi job description looks like. So similar to Makefiles, you define class and you have inputs. It's like requires method, have outputs, which is S3 file in this case. And we use it with our job queue Quentin, so no actual processing happens on Luigi's side. It's just used for coordination. It just submits jobs as Docker containers to this queue and synchronously waits for them. And a few lessons we learned from this. So yeah, as I said, it's not a hard problem. Lots of people, thousands of engineers solved it. But there is still need to solve it for 2001st time each year, apparently. Good thing when jobs depend on data and time-based scheduling is not hard, but complicates things unnecessarily. And ideally, you want to have idempotent jobs, so you can run them easily. So you just run same job twice, and if you have same inputs, you get the same output. It's not strictly always the case, because sometimes you have to pull data from external sources, things like that, but you kind of should try to kind of strive for it. And you should be able to run job twice, and it will just override existing data. Another thing that helps is, so we use success files, Hadoop-like, and S3 is to kind of as an indicator for job success or failure. So you want to have some kind of easy way to figure out if job failed or not, just as a whole. There should be no state when it's partially succeeded. And also kind of good thing to do is use S3 as a kind of write-only file system, object store, so we don't override the same files over and over days. We just create new set of files with each job run, usually, or like at least for the same day. You keep adding data. Make things really easy to debug, so you can always check your file for today is there. So it's like really bare bones, but you can just examine state of your data pipeline using AWS CLI or something like that, and it's pretty available. And as I said, useful to have dynamic dependency graphs when you can create new jobs from existing jobs dynamically. Next part about saving money, because when you have lots of R3 8X larges, they tend to cost a lot. And in some use cases, you really cannot afford this because your margin will kind of be too small because of the value you produce with those jobs. So we went for Spot instances, which is probably obvious answer on AWS. Probably save maybe like 80% by using Spot instances everywhere. Problem is, of course, that this is a spare capacity at Amazon data centers and availability varies. Sometimes someone big comes in and buys all the instances and kind of your jobs start to struggle. And all the things I said about S3 and keeping it simple and jobs to be runnable, it really helps when you have those Spot instances that can be taken away from you at any time. So this is how normal price graph for Spot looks like. I think it's R38X large. So normally you save a lot of money. I think the normal price is about $230. And most of the time, in this period of time, you would pay much less than that. But you do have those spikes. And if you're familiar with how Spot instances pricing works, you kind of set a floor, like your bid. You say, I'm ready to pay no more than $2 for an hour for this instance type. And in reality, you pay this market price. It's determined by Amazon by some magic, not really transparent. But I guess it's correlated with availability. And at some point, if market price goes above your bid, they just take away your instances and your jobs fail. So if you have this transactional logs in S3 and you have all the data checkpointed to S3 periodically, makes it pretty easy to use Spot instances. Worst things happen on spot market sometimes. This is a week in May when someone got into Amazon data center in Oregon. Someone big probably paid them a lot of money, but they also took away all the R38X largest from the market for a few days. That was a bit bad time for us. But still, you can work around this because there's many markets for each instance types, for each availability zone. There is a separate pool of instances. And if your jobs are not super tied to a specific instance type, you can often switch to a different instance type. So in this case, I think we even part of the jobs, we switch them to G2 8X large, which is GPU instance. We don't use GPU at all. It was just cheaper. It was even cheaper than like normal M3 something for the same amount of memory and CPU. So you kind of have to have some kind of insurance against that. And things you do is use multiple instance types. This is pretty easy. Next thing is to have multiple regions, which is a little bit harder if you have all your data in S3. If you use different regions, you have to pay for bandwidth, which can get expensive. But ideally, what we do is we compress all the data, like first step downloads logs, and store them in a really compact form. It helps a lot with performance, first of all, but if you have a smaller data set, you can probably replicate it to a different region and have your jobs run there if market price changes. And a good thing is to have a pool of on-demand instances, which I think we do to a small extent. Of course, there is still a bit of a caveat there. If there is nothing on the spot market, then there is no spare capacity. That means that you won't go too far with on-demand unless you reserve them in advance. But it's still worth it. In our opinion, you save lots of money doing that. And you don't have to hesitate to and use like smaller instance types. We just go for R38X large, which is 250 gigs of RAM. Makes life so much easier when you don't have thousands of smaller instances. But if you have just a handful of big ones, just way better performance and way better to write any kind of machine learning jobs because you don't have to care that much about distributing them and doing some kind of complex communication between your workers. And now putting it all together, so the bottom layer is Docker, so you can just package all your pieces of your code as Docker containers nicely and not care about deployment too much. For resource management and managing all the auto-scaling groups, we use Quentin, which is a queue service, but you may open source it, but you can probably build it pretty easily yourself, probably. You could use SQS and Lambda, and I think even Amazon has a blog post and something like that. The only thing is lacking is having some kind of UI and tools to inspect this queue in process when jobs are running. And for dependency management, we use Luigi. You could go for like Airflow, which is a pretty good tool. It has nice UI built by Airbnb. The only problem with it, I see that this time management thing, they kind of built in all the time-based capabilities, and I think it kind of introduces too many concepts, makes it a little bit more complicated than it should be. A few things that we found out that, yes, we don't use any kind of special storage distributed file system for this, like no Cassandra, nothing, just files in S3, works perfectly, reliable. You can pull 4 gigabits from a single instance. I think from S3, if you use the largest instance size, that has a 10 gigabit connection. So don't have to care about state, like Zookeeper going down, any kind of quorum. That's already taken care of by S3. So, and keeping jobs small, minutes to hours, really helps, but I think it's true for any batch processing system. You just want to be able to restart jobs if they fail, if spot instance goes away, things like that happen. You just want to be able to restart it and don't lose too much time and money. And that's 3 on EC2. So as I said, yeah, storing data efficiently, it's a really big deal. And if you think about it, all the big data problems, it's been a long time since term big data was invented. And since then, we got much better in terms of memory size and network. And unless you're doing something like, I don't know, Large Hadron Collider, or maybe photo recognition when you have lots of data, which is actually comes from kind of arrays of physical sensors. And that may be a big data problem. When your data is just some kind of user-generated, basically, I don't know, clicks, button presses, just stuff that people do behind the computer. I don't know, write blog posts. If you just take me, put in a room with the computer, and make me produce as much entropy as I can do, I won't go far. I mean, it will be maybe, I don't know, kilobytes, megabytes of data, and there's just 6 billion people out there, so you can compress this well in gigabytes, maybe terabytes range. And as I said, when you have your data set reasonably small, maybe not fitting in memory, but maybe terabytes, tens of terabytes, using bigger instances helps a lot because you save on all the communication and coordination of those jobs. You can just memory map all the data, and it just works. So just to back it up with some daily numbers, people love numbers, so we run hundreds of biggest spot instances daily. Yeah, probably sounds like about right, because we like start them for a few hours, crunches the data for a few hours, and we kill them. Yeah, they said 30 terabytes of RAM in this cluster, total at peak, hundreds of containers running, minutes to hours, hundreds of billion log lines analyzed daily. And we use lots of technologies. We don't have to hesitate and are not tied to any Java or Python or Go ecosystem. We just use whatever. Lots of C, Erlang, Haskell. We use D. Some people heard of it. Have some kind of custom D cells for some analytics jobs. So that's pretty much all I have today. This is the last session anyway. Everyone's happy. Thank you.